Feel free to ask any questions if you have them.
No, not right now. No questions.
No problemo. I'm trying to get my circuits drawn so I don't have to waste a lot of time during class doing it.
My brain is it's just I'm okay. I mean, my brain's fine. It's just like I've had linear algebra with proofs this week, and then I've had vector calculus and multivariable calculus. So I'm doing all those calculations again to the triple integrals. And
Yeah.
then I've got this class, and then my other class is probability and statistics, just the way it worked out for to finish up the last semester.
Right.
All of that got put in at once because normally I take like two, like science and math and two different kinds to sort of balance it out.
Right.
And all of these classes, they all have a lot to do with each other right now. The ones I'm taking this semester, so they all overlap. So I think it's kind of why my brain went blank at the test because I'm like, which one? I normally try to stay away from doing that much math in different classes all at once because I'm like,
Right.
what am I supposed to be doing with this? I just kind of got lost in the weeds with that one, you know,
Yeah, I think
because
it happens
I had
sometimes.
them.
Sometimes
Yeah.
you'll luck out and it actually turns out to be a little better when you have several of them at once. But like you said, sometimes it makes things worse.
Well, it's better now because everything is making a lot more sense towards the end of the class. But at the beginning, I was just trying to keep everything separate.
Right. Uh, hmm This is a pain in my butt. Ah, darn it. It keeps erasing everything. All right. Now we got everybody. Looking pretty good. And I got everything copied like I wanted to. Oh, I should probably address this. Let's see. All right. Well, it looks like we now have about 9 students in here. That's obviously not the whole class, but I guess it's good enough to have to get started because it is 22 after, so we technically need to get started. We are starting chapter 26 today, so I want to make sure you guys uh, follow what's going on. We are starting chapter 26. The homework for chapter 25, I believe, was due last night, but just in an attempt to help you guys out in case the end of the semester is getting kind of hard for you, I went ahead and moved it back to tomorrow night. So, or yeah, tomorrow night. So if you didn't get one of those chapters done, or either the chapter 25 conceptual or the chapter 25 homework, you've got another day. This one will be due on, I think I set it to 4/1. I don't, is that what it's, yeah, I guess it is supposed to be what it is because you guys meet on Tuesdays. We're starting chapter 26, which is basically called DC circuits. I'm going to streamline it to some extent in that I'm not going to cover all the derivations. For instance, I already covered the derivations of how to derive, how to combine capacitors in series and parallel, and that's sort of the same derivation for the resistors. And I've already given you the formula for the resistors in parallel and series. So we're going to do some stuff with that. The main thing we're getting to, though, is we're going to be working on DC circuits. And there's an area where you learn how to make a voltmeter or an ammeter uh, out of a what we call an ammeter. So you can actually take a ammeter. Actually, there's another name for it. It's drawing a blank right now. But anyways, a galvanometer. Sorry. So you can take a galvanometer, which is really an ammeter that measures a very small amount of current. You can take that and specify that it's going to be a voltmeter that handles up to 500 volts, or a ammeter that's going to handle up to 100 amps or something like that. So that's another process I'd like to teach you guys, but I'm going to sort of go through those quickly. The more important thing right now is that you learn how to analyze circuits, and that you learn the model that we use for a battery. So it turns out when you go and buy a AA, AAA, C battery, D battery, 9-volt battery, all those batteries, they basically come to you with a little bit higher voltage than they're nominally supposed to have. So, for instance, all the AA, AAA, C, and D batteries, they're all supposed to have a nominal voltage of 1.5 volts. If you open up the package of a brand new one and connect it to a voltmeter, you'll find that it usually reads around 1.68 or 1.72 or something like that. And the reason why is when you actually connect that battery to a load like a flashlight or a light bulb or something like that, the voltage that you're reading from the positive terminal to the negative terminal, which is called the terminal voltage, will drop. It'll drop from the 1.72 or 1.68. It'll drop to closer to 1.5. It maybe drops to 1.55 or a 1.5 on the money or something like that. So the way we model that is we imagine that there is some kind of ideal battery inside that produces what we call an electromotive force, an EMF. That's an old term that was used when we were first starting to discover what electricity and magnetism did. And we knew, of course, if charges are moving, there must be some force making them. So they named it electromotive force. Later, we learned that the force that makes them move isn't really a force, it's a electric potential called voltage, but we've kept the term. So we imagine this perfect ideal EMF source inside of the battery, and then just beyond that is a internal resistance, and we imagine that internal resistance grows with time, and that accurately models the fact that the terminal voltage goes down when you connect it to something, and it accurately models the life of the battery, because as you use that battery more and more, the terminal voltage will continue to decrease, and eventually it'll get to the point where it's not even delivering 1.5 volts, and you'll get a light bulb, for instance, that's not as bright as it's supposed to be. So that's the way we model it. And we want to start off with that, and then we're going to go into applying it to some very specific circuits. I've made up my own problems. They're very much like the ones in the textbook, but hopefully they're not enough alike where they would look like any kind of violation of law or something. So anyways, I'm going to go ahead and share my screen and work that through for you. So I'm hitting share screen, and now I'm going to select share screen here and open up my good notes. Okay. That should come available in a second. Tighten up my Apple Pencil. All right, so what I have drawn here is a circuit. Notice I've got little purple lines. That's supposed to look like a D battery or a C battery or something like that. And I did that on purpose because I wanted you to see how we interpret what the battery actually is. That battery that you see that has 1.50 volts by it, that's the EMF. Now, it's not really that accurate because we know the EMF would actually be more like 1.72 or 1.68 or 1.69. I just did 1.50 so you can see what would happen towards the end life of a battery. It's very typical for the internal resistance of a battery to start off around a half to 3/4. In other words, less than an ohm. Notice I did write the ohms here. In general, next to the symbol, there's no need to write that it's ohms unless you have like a kilo ohm. But even then, we don't write ohms. We'll just write a K if it's a kilo ohm, and we'll write nothing if it's a regular ohm. So this one I did include the actual omega. I'm not going to include it in general with these circuits, but you see that that EMF source has an internal resistance, the 0.70 ohms, and then the wire goes out to a load that's 50 ohms. So in this circuit, what we're going to try to do is calculate the terminal voltage. But the first thing I want to do is calculate the current. So I is equal to question mark. I want to calculate V terminal, which, as I already explained to you in words, V terminal is the voltage difference between, let me draw a dot on here, between this spot, you do the voltage there minus the voltage here. Okay, so that's V terminal. We'll call this A, for instance, and we'll call this B, and it's V A minus VB. And what we want to know is that. Once I have that, then I can go ahead and ask questions like, what is the power wasted by the 50 ohm resistor? And then what is the power wasted by the internal resistance? Like that. Okay. So that's the problems that we're trying to solve this time. Everybody understand what's going on here? All right, so what I'm going to do is I'm not even going to employ, just like your book doesn't, I'm not even going to employ the formulas for series and parallel. Your book just seems to treat it as if it's obvious that the voltage drop leaving the battery is going to be as a result of that internal resistance. And then there's going to be another voltage drop that's a result of that in 50 ohm resistance, and that the net resistance will in fact be 50.7 ohms. That's what we're shooting for here. So I'm just going to use that as if we know that. Okay. Later, I'm going to actually use the formulas for parallel and series and all that good stuff, and we'll get a couple examples of that. Okay. All right. So let's start solving it. So here's our solution. What I know is V is equal to IR, and that applies to basically everything. But if you're treating R as a constant, we say that it's applying to only ohmic devices, which are what these resistors are supposed to be. In principle, though, any resistor has a maximum power that it can dissipate, and if you exceed that power, it's no longer going to be ohmic. It's probably going to get ruined and act really quite irregularly. But what that means is the voltage of the entire circuit, the 1.5 volts, is equal to the total current I times the total resistance, in this case 50.7. So that's one case, but you also have the voltage across the resistance of 0.7 ohms. That's equal to the current through that resistor times 0.70 ohms. Similarly, there's a voltage across the 50 ohm resistor. That's the current times the 50 ohms. So we're going to work with that. Let's start off with the current. What I say is 1.50 volts is equal to I times 50.0 ohms plus 0.70 ohms. You can see the pointlessness of me adding a second decimal place to the 0.7 ohms. You also see that in this case, I'm solving this problem probably more like a lot of my students do. I like to solve the problem algebraically and then plug in the answers. In this case, I'm actually plugging in the numbers and then solving for it. So in this case, I'm going to get that the current is actually equal to 1.50 volts divided by 50.70 ohms. And notice I underline that second zero, or that second decimal place, because that's not really a significant figure, because when you add the 50 and the 0.70, the 0.70 is a significant digit only for the 0.7 and doesn't cover the 50.0. Okay, so I'm going to do 1.5 divided by 50.7. That gives me 0.2959. 0.0, sorry, I didn't say the second zero last time. 2959. Okay. Now you can see from this, I've got 3 sig figs divided by 3 sig figs. So really this last digit here is not a significant figure. And this is actually in amps. So we can say that I is equal to 29.59 milliamps. Okay, that doesn't mean I'm necessarily going to use the milliamps, but I did express it that way because it requires less zeros and all that good stuff. So that's the total current going through the circuit, and we treat it as if it's a conventional current, which means it travels the direction that positive charges would flow, and we know that positive charges tend to run from the positive end of a battery. Now I'm going to go ahead and calculate the voltage of the terminal voltage of the batteries. So what I want you to realize, and I do this a lot, you can actually take a multimeter like the ones you've been using in lab, and you can actually set it up to read certain things. So what I'm going to do is imagine a little multimeter right here. Okay. And I'm going to imagine this multimeter is actually set to read volts. And in this case, DC volts. So I'll put V with a bar over it. I'm also going to make a red connection here and write V omega, because you know that's what the red terminal was in class. And then we had a black one that was called COM, meaning the common one. Okay. So I can take this wire, and I'm going to do it purple just to make sure it stands out. Actually, let me do it in green just to make sure it stands out. I'm going to take this COM terminal and apply a wire to it and then connect it right here. Okay. By connecting it right there, I connected it to the low voltage side of the battery. And just like last semester in chapter, let's say chapter 8, you were actually able to set the zero of potential energy anywhere you wanted. You can set the zero of electric potential anywhere you want as well. And the way you do that is you normally just add a ground. And what a ground looks like in electronic circuitry diagrams is something like this, or sometimes you'll see just an arrow like that. Both of those are grounds. So what you could do if you wanted is to hang a ground right there where I got the little green wire connected, and that's always allowed. Okay. The main thing is I'm trying to tell you that I'm going to consider that to be 0 volts. So if I took both the COM and the V omega and put it there, obviously the volts would be 0. And that's relative to the COM, which is set at the exact same place, so it has to be. Now the other thing is I can take this this V omega pole, and in this case I'm going to jump it across here just so I can see where it goes. And if I put it right here, notice it's to the left of the positive terminal, and in fact it would read 1.50 volts. Okay. Now, the way I normally do this is I don't take time to write all those, to draw that big multimeter. I generally just draw a little bubble. And that's what I'm going to do mostly. But I wanted to show you again, though I think I've showed you plenty of times, what this is. So right now we've got that one. What I would like to know is, what is this bubble? Now, what we know is that resistor, that internal resistance, has a voltage given by V internal resistance. Actually, let me write that as V 0.7, okay, is equal to I times 0.70 ohms. That's going to be a voltage drop. And remember, voltage drop in the direction that current goes. So the current we said was going to the left. That means the battery side of the resistor is higher voltage than the other side of the resistor. So this is going to be a decrease in voltage in going from where the ohm meters, or excuse me, where the multimeter is connected to where the little blue dot is. So when I calculate this, I'm going to say 0.02959 amps times 0.70 ohms. Actually, yeah, 0.7. So when I multiply that, I get 0.021, or 0.0207 volts. Okay, so what that means is the voltage drop from the left side of the internal resistance to the right side of the internal resistance is 0.207. And since it was 1.5 on the right side of the resistor, notice it's just a small bit of wire between the green dot and the left side of the internal resistance. So that resistance is negligible, though in practice, if we had a voltmeter that read at 1,000 decimal places, it'd probably detect a slight difference in voltage between the dot that's right up against the battery and the left end, or excuse me, the right end of the internal resistance. Okay. So with that in mind, I'm going to say that the voltage at the green circle is going to be 1.50 minus that 0.0207. And when I do that, I get 1.47 0.9493. So I'm just going to say this number is 1.4793 volts. Now, again, that is relative to the ground side of the battery, because remember, that's where our COM is connected. When I write these bubbles, I'm pretending the COM on the voltmeter is actually attached right there to the right-hand side of that battery. And this bubble is wherever is attached to wherever the red side would be attached. So in this case, I can now say that the voltage on this side is 1.4793. That's 2 extra sig figs. So I'm going ahead and underline that. And if I put a bubble over here, whoa, if I just erased everything right here, if I put a bubble right here, it would read 0 volts. And actually, I need to put that in green since that's what I've been doing. So that's 0 volts. And that tells us that V terminal, which is 1.4793 volts minus 0.0 volts, that's going to be 1.47, and I'll just carry one extra sig fig, 9 volts. Okay, so we can see that in fact the terminal voltage is a little bit less than the EMF when you got a load going through it. That's exactly what I was telling you earlier. It's typical to be 1.72 or 1.68, and then when you connect it, it's going to drop back down to closer to 1.5. Any questions on that part? Okay, so that's how you calculate a terminal voltage. It just has to be uh, basically the voltage difference between one side of the internal resistance, the side that's farthest from the battery, and then the opposite side of the battery. So that's the total terminal voltage. Keep that in mind. Now that we have that, we can also calculate the powers that I wanted to calculate. So we asked to calculate the power wasted or dissipated by the 50 ohm resistor. And we know P is equal to IV. So I could write that up here. P is equal to IV is one result. We could also write I squared R, or we could also write V squared over R. All those are reasonable. The best thing to do is to use what you know. So for instance, I know I and R because I is the only current going through the circuit, and therefore it's always the right one. So I'm going to use I squared R, where R is the resistance of the 50 ohm resistor. So I'm going to write 0.02959. Again, I've got extra sig figs there. The 9 is not a significant figure. That's going to be squared, and then I'm going to multiply that by 50.0 ohms. So 0.02959 times 50 gives me 1.4795. And that is a ton of digits. We had 3 on the left, we had 3 on the right, so these two guys are extra, and that comes out to be watts. And that's what I'm saying is the power dissipated by the 50-watt resistor. Any questions on that? Okay, now we're going to calculate the power on wasted by the 0.70 ohm resistor. This is, in fact, part of the model is that we can now understand to some extent why batteries get hot when you're using them. I'm sure you've probably noticed when you're holding your cell phone and you're talking on it, after a while, the cell phone will actually get hot. So that's part of what that is. Your cell phone has an internal resistance as well, even though it's not strictly speaking a real resistor in there. It's just, the nature of the chemistry and physics going on. In this case, again, we're going to say 0.02959 amps. Oops, I don't think I squared that. I'm pretty confident yep, I did not square that. Back her up, folks. Hold on, hold on. Obviously Shonda made a mistake. Sorry about that. Can't take her anywhere. 0.02959. Let's square it this time since Shonda was so derelict and didn't do it last time. And I almost multiplied by 0.50 instead of 50. So I got 0.202959 squared times 50. This will be a lot better. That makes a lot more sense. I thought that was a huge amount of amount of watts being wasted. In this case, it is 0.04378. God darn it. Watts. Okay, sorry about that, everybody, but that's the actual wattage. Again, I got to do the same calculation here, and hopefully this time I'll remember to actually multiply it by the current squared. So again, 0.02959 squared times this time it's going to be 0.70, so I only get two sig figs, and that's going to be 0.00. Holy crap, this is really small. This is three zeros now, followed by 6129. Yeah, 6129. Okay, and we only get two sig figs, so they're wrong. Okay, we can also write this as 6.129 times 10 to the negative 4 watts. So that's another one. And this is equal to P 0.7. So just so I have the actual symbol right next to the answer, so it's quick and easy to look back and see what it is. Anybody have any questions on that? That's pretty straightforward, right? It's easy peasy. And let's see if Shauna can kind of behave herself this time. Sorry, she's the person whose name I know, so I'm gonna pick on her today. Actually, I've got all your names up here, so I can pick on Micah and Brandon and everybody. You see Johnny and Mikey and all right. Here's a neat question as well. So this is one that I actually did take it from your book, but I like it. They're suggesting in your book they're doing something similar. They're actually assuming it's a car, and they're telling you the voltage is 12 volts because batteries of cars are often 12 volts. I like to do this more symbolically so you can sort of see exactly what's going on, and you can analyze it. So what we're trying to figure out here is which one of these configurations, the left one, which is two headlamps that are in series, meaning headlights for a car, with a 12-volt battery, are two 12-volt, are two headlights that are in parallel, but connected to a 12-volt battery. Which one of these makes the brighter light? That's really the question here. The brighter light, which by the way is a little bit uh, problematic because you might think that the power is the light produced. Now, there is some, are you aware that you have a halo, John? The green thing? That's great. I didn't realize that was going on. Uh, anyways, when you actually connect this, you actually do have one option of it being in series and the other option of it being in parallel. And what we're trying to do is figure out how bright they are. Now, the power that's dissipated by this quote unquote resistance, because that's really all we interpret a light bulb to be, is a non-ohmic resistor, but we often treated it like it is ohmic, at least for short, calculations, short and quick results. What I will tell you though is the light that's put out by it, the brightness of that light is directly proportional to the power. And if you calculate the power of the two light bulbs in one case, and you calculate the power of the light bulbs in the other case, and one case is twice as much as the other, then you can pretty much assume the brightness of the light would be twice as much in the one as it is the other, even though it's not necessary anywhere near the power that it calculated. It's not unreasonable for an incandescent light to have 90% plus of the energy wasted as heat instead of light. So that's part of the other part I'm trying to make here. So what we're going to do is we're going to realize that in the case on the left, well, actually, let me write this first. Which configuration results in more light being produced? Sorry, I was running out of space and my letters got really skinny. So I'm going to go over here to the right and say or to the left and say solution. What we know is the total resistance, R total, for this left-hand configuration is 2R because they're in series, and we know that the rule for series is R1 plus R2 plus dot, dot, dot. Okay. Now that we have that, we can also say that I from V equals IR is equal to V over R. In this case, R total. Now, in this case, the voltage is not the same as the voltage of the battery. Can anybody give me an idea what you think? Can anybody give me an idea what you think the voltage across one headlight is in the left configuration?
V half, like V over 2.
Exactly. By symmetry, you expect both of them to decrease the voltage. And since they're supposed to be identical, which is what we're doing here, then it doesn't make sense except if both of them do the same. So in this case, what I'm going to say is the voltage for a single light bulb, so I'll write SL, is V over 2 divided by the total resistance. And the reason why we're using the total resistance, of course, is actually, no, hold on. Yeah, okay. So I just wanted to make sure. In this case, I don't want to do it this way. Yeah, let's kill this. Actually, I can't believe I just started doing what I was doing. It is important to realize that the voltages are different, but what I'm trying to calculate right now is the voltage for the entire, I mean the current for the entire circuit. So that's where I went wrong. I got sidetracked by making jokes and stuff and not paying attention. So we're going to calculate I total. So I'll put a capital T on it. Maybe that'll make me remember and help you understand. So this is I total that's coming out of here. Okay. Now, when I do that, of course, the voltage is V and the resistance is, of course, 2R. So now I have the current and I have the resistance. So if I want to calculate the power, I can say power is equal to I times V. Okay. So for a single bulb, I'll say SB, single bulb. In that case, the current going through it is V over 2R. And then the voltage across it, we decided was, in fact, V over R. So I end up getting V squared over 2R squared. Let's see, V over 2R, that looks right. Voltage, oh, I said V over R, not V over 2. I was wondering why I was getting an R squared in the bottom. That R squared is not supposed to be there, but that's because I wrote V over R instead of V over 2. So it's V over 2, and that's going to make this not V squared over 2R, but V squared over 4R. Okay, so that's the power from one bulb. Therefore, the power from both bulbs would equal 2 times the power from a single bulb, which gives me basically V squared over 2R. Okay, so that's the power from two bulbs. Now we can do the same thing over here. Of course, on the right-hand side, we know that 1 over R total, because they're in parallel, is equal to 1 over R plus 1 over R, which of course is 2 over R, which means R total is equal to R over 2. Now that we have that, we can find that I total, again, I total is here. We can find that I total is V divided by R total. And that gives us V over R over 2, which is 2V over R. Okay. Now, can anybody tell me what the voltage across a single bulb is? Again, we're doing the right-hand configuration. it might help you to think what are
Is it 2V?
not quite.
Oh, sorry.
What about, but no, I appreciate it. But what configuration are these two light bulbs in? Is it series or parallel?
Oh, well, they're in parallel.
And okay, when they're in parallel, do we know anything about how the voltages
Oh,
in the
the
two are
voltage
related?
is it's just V.
There you go.
Yeah, sorry.
Exactly. Yeah. So each of those have the same voltage, and obviously that's V. The reason why it's V is really you could look at it, the battery's in parallel with it as well. So if you think about it in terms of my bubbles, you could say the voltage over here is V. You can say the voltage over here is 0 volts. And then you can follow this bubble all the way along to here. You still get 0 volts. And all the way along to here, you still get 0 volts. And you can also follow the other bubble all the way along to here, and you still get V. And all the way along to here, and you still get V. So yeah, the voltage for a single bulb is in fact V, but I wrote it in red because I'm a goober. Okay. So now when I can do the power for a single bulb, that's going to be I times V. What I found out was that the I was in fact 2V over R. And what I found the V was just V. So that gives me 2V squared over R. The power, however, for two bulbs, it equal twice the power for a single bulb. And of course, that gives me 4V squared over R. So what we see is the power in, let's say, parallel divided by the power in series is actually equal to 4V squared over R divided by 1/2 V squared over R. You can see the V squareds over R's cancel out, and I get 4 divided by 1/2, which is in fact 8. So this means the bulbs in parallel produce about 8 times more light. Now, we were making certain assumptions that aren't necessarily all that valid. For instance, I can guarantee you, even if the light bulbs are identical, if you put 12 volts on one of those light bulbs, you're going to get a different resistance than you putting 6 volts on a light bulb. So the resistance would actually be different in the left-hand side than it is the right-hand side. But this is a good first-order approximation. That makes sense?
Yeah, Professor Younger, I got a
Yes, sir.
question.
Uh-huh.
So, the current total, it's 2VR, and both of the bulbs, they're in parallel. And I'm pretty sure, well, I'm gonna make a node A on that left side, right? And then node B on the right side of the resistors. I, I think the current, entering the node should be the current leaving the node. Um, I think that current should be split up between each resistor.
Oh yeah, thank
So
you.
yeah,
I've completely missed that. Thank
yeah.
you. Yeah, that was stupid. Nice. So it might actually be a factor of 4. I don't even know what I was thinking. Remember, that's I total. Micah's exactly right, everybody. I don't even know. And
It's
that
like
what's
a
worse is
Kirchhoff's what is it, current law
junction
or
rule.
something.
Or nodal rule or whatever. Yeah. Yeah, exactly. And what's worse is I'm pretty confident I made the same mistake in lecture because I completely was not paying attention. But yeah, you're right. The I total, let's say it's 2 amps. Well, if I total comes out of that battery on the right, then half of it's going to go to the first resistor, to the first light bulb, and the other half's going to go to the other light bulb. So in fact, I'm going to put an X like this and say it's actually going to be 1/2. Well, the I total is still right. Let me undo that correction. What I have to realize is this one is I total over 2. So I should put a 2 in there, and then that's going to make this guy disappear like that. Okay. Now, instead of 4, I get 2 times 1, which is 2v squared. And therefore, instead of this 4, I get just plain 2. And 2 divided by 1/2 is 4. So my answer should be, I am so sorry about this. This is really a horrible mistake. I can't believe I did it. But yeah, he's absolutely right. So the answer is actually about 4 times more. My fault. I don't know why I did, but it's really bad because I did it yesterday in lecture two. So sorry about that, everyone. Let's recap just in hopes that I can redeem the possible teaching that you actually received. In other words, I don't like giving you something that's erroneous. So what we did was first analyze the left-hand side. What I found was that because they're in series, the two resistors have a net resistance of R plus R, which is 2R. So that part's correct. I'll put a little check by it. The total current is the current leaving the battery, and that is the total voltage, which is the battery's voltage divided by the total resistance, which is the 2R. So I do get V over 2R for the actual total current. Now, in this case, they are in series, so the current doesn't have anywhere to go. So the whole current is actually going here. So we can say V over 2R is in fact the current through one of them. And then the voltage, which I did take time to correct for the fact that it was two of them, unlike the other side, that's V over 2. So that checks. Now when I multiply that, I get V squared over 4R, and that looks pretty good. Okay, so this result is fine. Now, as I said, the power from 2 bulbs is twice the power from 1 bulb. So I'm going to say 2 times V squared over 4R gives me V squared over 2R. So I'm going to say that one's correct. Everybody follow that left-hand side calculation? Any problems on that? Okay. Now, the right-hand side, what we were supposed to do was, again, find the total resistance so that I could find the total current. The total resistance, since they're in parallel, is added reciprocally. And in so doing, we find that 1 over R total is 2 over R. And therefore, R total is R over 2. So those are correct. The total current is correct by is correctly found by dividing the total voltage V by the total resistance R, and that gave us 2V divided by R, because R over 2 divided by R over 2 is the same thing as multiplying by 2 over R. So that I total is correct. What went wrong was when we did the other part. Now, the voltage across a single bulb is in fact V, and that's true for each of them, and that's because they're in parallel. So let's say, just to explain this, because they are in parallel. Okay. Now here's the part. What we have to realize is the power for a single bulb is the current going through that single bulb. And if I have IT going through or leaving the battery, then by symmetry, each of these guys are going to get half as much. So what I could do here is say that this current right here is I total over 2. And I can say that this current right here is I total over 2. And that's what I put in after I put in the red mark anyways. So we had calculated 2V over R for the total current, but I had to divide that by 2. So that's why the little R is in the denominator in that parentheses in red. The voltage, of course, is still V. So when I actually multiply that, those two 2's cancel out, and I get V squared over R. And then again, the power by 2 batteries is twice the power of a single, or excuse me, by 2 bulbs is twice the power of a single bulb. So I have to multiply the V squared over R by 2 to get 2V squared over R. And that checks that and that. Now I just, as a good way to actually think about how related they are, it's often good if you have two exactly the same quantities. In other words, 2 powers or 2 works or 2 energies or 2 joules or 2 currents or whatever. One way to discern one from the other or say how much stronger one is than the other is by dividing them. So I chose the larger one divided by the smaller one, which is the norm. You can also do it the other way, but then you get a fraction. So I took the large one divided by the smaller one and let everything cancel out, and it just gave me numbers so that I could reinterpret this whole equation. Notice this whole equation right here basically says that P in parallel is equal to 4 times P in series. So that's another valuable tool that I wanted to show you with this, even though I've probably done it a couple times in the previous semester, and I don't think I've done it any this semester, but I know I've done it last semester. So that's just another common tool that helps you figure out how things are related. So like if I ever asked you for the acceleration of gravity on the surface of the Earth compared to the acceleration of gravity on the surface of the moon, you might want to calculate the power of gravity or the gravitational acceleration on Earth divided by the gravitational acceleration on the moon, and you'll get a lot of cancellations and ultimately just get a number. So any questions on that? I apologize again for that, and thank you for catching me, Micah. I really appreciate that. That was example 2, by the way. I didn't number my examples this time, but I should, just in case anybody ever contacts me and tries to ask me questions about it. Here's example 3. So this is another one, and what we can do here is I'm going to take, I haven't decided what voltage I'm going to put on this. I think I'll just put a 12-volt battery. Let's call this 12.0 volts. Okay. This is a problem where we would like to know what the equivalent resistance is. So I'm going to write what is the equivalent resistance of this circuit. So that's the question. I'm going to add some other questions too, like what is the velocity across the 4 ohms, or excuse me, the velocity, good Lord, the voltage across the 4 ohm resistor, the voltage across the 5 ohm resistor, the voltage across the 6 ohm resistor, and what is the total current, and what is I4, what is I5, and what is I6. So let's just nuke the crap out of this. Let's really figure out everything we could possibly do. Okay. Your book actually does something like this and then does a couple of parts like calculating power or something like that. But and it's a very similar problem. I think I use different, entirely different resistances though. So let us begin. Solution. So what I'm going to be using here largely is V equals IR, which is Ohm's law, of course. We also have 1 over R equivalent in parallel is equal to 1 over R plus 1 over R2 plus dot dot dot, and we have R equivalent in series is R1 plus R2 plus dot dot dot, and that's pretty much all we really need. Of course, we're going to need to understand principles like the fact that voltages of objects in parallel are equal, currents of objects in series are equal, that kind of stuff. Okay. So when you have a problem like this one, and this one's much simpler, what you want to do is find 2 or more resistors that you can immediately apply a formula to reduce it to a single resistance. In this case, the 5 and 6 jumps out. So what I'm going to do is I'm going to say R5 comma 6 is given by 1 over R5 comma 6 is equal to 1 over 5.00 plus 1 over 6.00. Of course, we know that 5 does not go into 6, so that makes 6 not a good common denominator. 6 times 2 is 12. 5 doesn't go into that. 6 times 3, no. 6 times 4, no. 6 times 5, yes, that always works. So we're going to multiply the 1 over 5 by 6 over 6, and that'll give us 6.00. And then we're going to multiply the 1 over 6 by 5 over 5, so that'll give us 5.00. And all that will be divided by 5 times 6, which is 30.0. Notice 5 times 6 only has 3 sig figs, so I had to make that 30.0. So in this case, we end up having 11.00 over 30.0, and 11 divided by 30 gives me 0.366667. Now, that's not the r that we want. In fact, the r that we want is the reciprocal of that. So I'm going to raise that to the -1 power, and that gives me 2.727. So 2.727. That's 4 sig figs, which is more than we should have. So I'll just write an underline there and call that omega. And what that means is we can replace these two guys with 2.727 ohms. So that's helpful. Anybody have any questions on that part? Okay, now what we have is a 2.727 ohm resistor that happens to be in series with a 4.00 ohm resistor. So I can say R 4 comma 5 comma 6 is actually equal to 4.00 omega plus 2.727 omega, and that gives me 6.727 ohms. So that's the entire resistance. So we're going to say R equivalent is in fact equal to R 4 comma 5 comma 6, which is 6.72 with that extra sig fig there that we can use later. So what we're saying now is we basically have a 12-volt battery connected like this to a single resistor whose resistance is 6.727 ohms. And of course, that has a current I going through it, which I'll call I sub T for I total. So now I can see that I total is equal to, oh, and I forgot to write this down here, so I think I made it, yeah, I did, 12.0 volts. So now I can write 12.0 volts divided by 6.727 ohms is equal to 4.4 amps. Now, that's not enough sig figs, but that's all I could fit in there. So I'm going to go ahead and write I total is equal to 4.40. I had 3 sig figs and 3 sig figs. So that's really all I should have. So that would be 4.400 amps with one extra digit beyond what's significant. So I now have that. Now, here's the part where I was talking about the bubbles helping you. Okay, so I'm going to draw a bubble right here and call that 0 volts. I'm also going to realize that it's only wire between that spot and, let's say, this dot or even this dot and this dot. So in fact, I'm going to say the voltage here, the voltage here, and the voltage here are all 0 volts. Everybody follow my argument there? If I actually had a multimeter that did an infinite number of decimal places, there's a high probability up there at the 5 and the 6 ohm resistor where I have those red dots, they might actually be a voltage of 0.00001 or something. right? Because in fact, there is a slight resistance in the wire. If it wasn't, no current would flow from the 5 and 6 ohm resistors to the other side of the battery. So there has to be
Excuse me,
some.
Professor Younger.
Yes.
I don't know if you calculate I total correctly. It should be 12 volts over like about 6.7 ohms. That should be
Did I
like
not?
two-ish,
What did I
two-ish
divide it
amps,
by?
I think.
Oh, Jesus.
Yeah.
That's
I,
not
I
good,
was
is
just
it?
doing the calculation. I got like 1.784 amps.
Thanks. Actually, it was weird because I was thinking I was surprised to find that it would even be whole amps, much less 4 of them.
Hmm.
So thanks for catching that. So
Yeah.
evidently I wrote down what's right, but what did I calculate? Oh, yep. I never added the 4 to the 2.72. Thank you for that. Let's catch that again. Okay, everybody, I'm erasing this 4.4, and Micah will be teaching class next time. Seriously, guys, I apologize, and I want to
Oh
thank
my
Micah for
God, please no.
that.
As long as it's not shot.
Wouldn't that be great? It would be a lot worse, trust me,
I do
for
not
me.
think I am ready to teach this class.
Thank you, bud. 6.727. That's what I had. Yeah, okay. Yes, that gives me 1.783. Okay. Thanks for catching that again. Everybody, please make your corrections, and uh I apologize. Feel free to smack me in the head when you do my evaluation, because clearly I'm smoking crack. So my answer, and I'm lying, I do not smoke crack or do any kind of, drugs or anything like that. So, so this is 1.783. That's 4 sig fig. So I've got 1 extra sig fig there. Thanks again. All right, everybody catch that? Thanks for backing me up there too, Micah. That's excellent when people are doing the calculations alongside of me. That saves me from making careless boo-boos like that. All right, here we go. So now that I have that, does everybody agree about the 0 volt conclusion that I made for all those little red dots? So it's just basically saying that, hey, a wire has very little resistance. So in order to detect a difference in voltage from the 0 side of the battery to the other thing, it'd have to be like 3 or 4 decimal places out. Now I can do the same thing here and say, ooh, I can just erase everything. That'd be cool. I can do the same thing here and put a bubble right here, and that's going to say 12.0 volts. But notice that's only a wire away from this red dot, this red dot, this red dot, all the way up to this red dot. So what I can say is the voltage right there at the left-hand side of the 4 ohm resistor is 12 volts. That helps me because I can now use Ohm's law to figure out what the drop in voltage is across that 4 ohm resistor. So now I can say voltage across the 4 ohm resistor is equal to the current that goes through it. And notice the current I total that goes to the left here, that doesn't have any alternate choices. So every coulomb that goes, that leaves the left-hand side of that battery has to go through the 4 ohm resistor. So you know that the 4 ohm resistor gets I total. So I'll put that in there. I total is 1.783, but Micah thought it was 4.4 because he's a crackhead. But we corrected that.
I think I'm too broke to get correct.
Exactly. We're just not wealthy enough, right? All right. So this was going to be this times the 4.00 ohms. Let me know if I offend you guys. I'm just playing around here and I'm trying to keep it entertaining.
I'm not rich like Younger.
You don't make teacher salary, do you? So I'm going to take this 1.78 and I'm just going to multiply it by the 4, and we're going to pray for the gods of mathematics to shine upon me. So 7.135 is what I get. Hopefully someone else might verify that. I'm pretty sure Michael's giving it a try. So what that means is the voltage across the 4 ohm resistor is a drop in going from the left side to the right side of 7.14 volts roughly. So I'm going to write this as V4. So we've got yet another answer. But that's wonderful because if you take 12 minus 7.4 or 7.135, whatever the answer is, you get 4.864. So if I do 12.0 volts minus 7.135 volts, I get 4.86 5 volts. And what that means is right here. Whoa, no, there I go again, erasing everything. Right here, the voltage is 4.865. So that's the voltage there. But again, using our argument from wires, that's also the voltage here. And that's also the voltage there. So at the left-hand side of the 5 ohm resistor and the left-hand side of the 6 ohm resistor, the voltage is also 4.865. Everybody follow that? Does that make sense to everyone? Now, look, we know the voltage on the right-hand side of the 5 is 0, and the voltage on the left-hand side is 4.865, and the same thing with the 6 ohm resistor. So V5 and V6 are known. So I can finally say V5 equals V6 is equal to 4.865. Again, the 5 is an extra digit here. And I'll put volts there. And that's our answer. Anybody have any questions on that? All right, now we can go through and start answering the current questions. So I4, I think we've already established what that was. Does anybody remember what I4 should be? It's more important that you really understand what I4 is.
It should be like I total because it's in series, right? Yeah.
Exactly. There's no alternate path from the positive side of the battery going around the 4 ohm resistor. So everything that leaves the battery has to go through the 4 ohm resistor. So I want to say I4 is equal to I total. And of course, that's 1.78 extra digit 3 amps. So we got that. Now it's really easy. There's a really easy way to figure out the current through the 5 ohm resistor. Namely, we know the voltage and we know the resistance, so we can just do that. So that's good, but check this out. What we know is that the current going into the junction that splits off and makes a 5 and 6 ohm resistor, I'm going to do it a harder way for more intense problems. Okay. So I'm not trying to confuse you here. You can readily say, I'll show you the easy way and we'll actually put it down for an answer and then I'll show you the hard way. So I5 we know is going to be the voltage across 5 divided by 5.00 ohms. And we already know the voltage across 5 is the 4.864. So if I divide that by 5, I get 0.9729. Whoa. 0.9729 amps. Now that's supposed to be 3 sig figs, so that 9's an extra. We know that's the actual answer, but what I want to show you is there is in fact another way, and this 5 looks really bad to me, so I'm a little offended. There is another way that when you're doing a more complicated circuit would save you. So what I'm going to do is I realize that, let me draw in black here. What I have is a wire coming in that's carrying a current of 1.783 amps. Okay. And then that wire is breaking up into 2. Okay. This is going to be, for instance, I'll do a purple just to make it different. This is going to be I5, and this one's going to be I6, right? So what I know is I total is equal to I5 plus I6. That's just conservation of charge, right? If you say 100 coulombs are going through the 4 ohms in like a millisecond, then what you know is if the 5 ohm resistor has 20 coulombs going through it in a millisecond, then clearly the 6 has to have the other 80. So that is one thing we're going to say. So I can write this like this. I could say 1.783 amps is equal to I5 plus I6. But we know something else about the relationship between I5 and I6. I5 and 6, in other words, the I shouldn't say I5, the resistance 5 ohms and the resistance 6 ohms are in what kind of configuration? I'm looking for a word like series, parallel, none of the above.
Oh, we're asking about the 5 and 6 ohm resistor. They're in parallel.
Exactly. So that means, oops, there I go erasing again. So that means, I'll put an implies, V6 is equal to V5, which implies I6 times 6 is equal to I5 times 5. Now, I would normally put the omega there for the units, the ohms, but I don't have room, so I just put it there. Does everybody agree with that? So this tells us that I6, for instance, which actually let's do I5. I5 is a small, the resistance of the 5 ohm resistor is smaller, so it should get the larger current. So if I solve that second expression for I5, I'd see I5 is 6.00 over 5.00 times I6. And now I can plug that into my conservation of charge equation. So now I'm going to say 1.783 amps is equal to I5, which is now 6/5 I6 plus I6, which of course is equal to 6/5 plus 6/6, which would be 12/11. Ooh, 6/5 plus 5/5. Sorry about that. So 6/5 plus 5/5 would be 11/5 of I6. So I6 is in fact 5 over 11 times 1.783. And of course, we know we had 3 sig figs, so we can just round it that way. So I'm going to 1.783 times 5. And then I'm going to divide that by 11, and that's going to give me 0.8105. And that's I6. Now, that's not the one I'd already calculated the easy way, but that's okay. We can now use the other expression to get that one. But there's a whole new way that I showed you where I didn't have to, I didn't use the easy way. I actually found a way to do it. The I5, on the other hand, oops, I should probably use the blue. So I5 in this case is actually equal to 6.00 over 5.00 times the I6, which is 0.8105 amps. So I'm going to say times 5 divided by 6, and that gives me 0. Oh crap, how did I get that wrong? This one's given me,
It should be 11 on the bottom, I think. So it's 6 over 11.
oh yeah, thank you, that's right. Oh, wait a second. Did I do that when what I'm looking at is this expression right here. Everybody see that I just wrote? I'm gonna put a red dot next to it. That little thing, when I found out I5 was 6 over 5 times I6, that should allow me to figure out what I5 is by multiplying 6 over 5 times I6. Did you get the same thing I did, Micah, when I got to 0.8105?
Yeah. I did current division for it. So that I5, it should be 6 over 11. Yeah, and then you would get 0.9. So,
So did I screw that up on the other part? Let's see,
oh
V5.
no, you did it right on the other part. Yeah.
Oh, did you get the same 5 I6 as I did
Yeah.
though?
Yeah, 0.81 amps.
Gotcha. Okay, so that looks about right. And did you ultimately get the 0.9729 that I got as well?
Yeah.
Okay.
Yeah.
So that works at least. All right. So I don't know exactly what went wrong with this, but anyways, you can get that. Yeah, that's, oh, I see right now. I had multiplied by 5 and then divided by 6 instead of doing the opposite. So that's why I got the wrong answer. Ooh, thank God. I was like, man, I'm not understanding at all how this happened. So I'm going to do 0.8105 times 6, and then I'm going to divide that by 5. I did times 5 and divided by 6. Yep, 9726. I'd made so many mistakes. I was confident I just made another mistake, which I did, but not as bad as I thought. So 0.9726 is what I get to 4 digits, which again is one extra sig fig. So notice in this case that I actually got it correct to all the sig figs. Any questions on that one? All right, so that's sort of the nasty. Okay, everybody understand how we did that? And that's actually a really modest problem. That's not a difficult problem, believe it or not. Okay, this next one is a somewhat difficult problem. I think I need to get to the Kirchhoff's loop rules, though. I think I'm going to skip this because we only got 10 minutes left. And I think I need to get to the Kirchhoff's rules. So I'm going to skip this one. I'll do it and post it later. And in fact, I probably already did something just like it several times on my YouTube channel. But I'm going to do this one later. I'm going to do this one right now. Now, you can look in your book and you'll see that it's got Kirchhoff's loop rule and Kirchhoff's junction rule. Kirchhoff's junction rule, I'm just going to verbally state it, is that at any particular dot where 3 or more wires come together, okay, you got to have 3 or more coming together, some fraction of those wires will be carrying currents into the dot, and the other remaining ones will be carrying current out of the dot. The key point on Kirchhoff's junction rule, which is really just a conservation of charge rule, is that the sum of the currents coming into the dot is equal to the sum of the currents coming out of the dot. So that's one big rule. It's highlighted in the book. I shared it with you guys so y'all can find that. Now, Kirchhoff's loop rule is different, but it basically is related to that math I told you before, where if you take the closed integral, it's always going to be 0. That's basically what's happening here. So what Kirchhoff's loop rule says is if you add all the voltage increases and decreases along a closed loop of a circuit, no matter what loop you use, the sum of all the additions and subtractions of voltages will be 0. Okay, that's part of the rule. Now, the caveat to that is you need to understand that when you traverse a circuit in the direction of the current that you chose, because I actually took the time to write the current directions on here, but that's not required. You should be able to make them up on your own. And it doesn't matter if you get it wrong, they'll just come out negative for whichever ones you got wrong. But the rule is if you traverse a leg of a circuit in the direction of current, then a resistor will be a voltage drop. But if you go the opposite direction, then it's going to be a voltage increase, which is weird. You know, you're thinking of a resistor that should be a voltage drop. But no, guess what? If you're going the opposite way, it's going to be a voltage increase. The other caveat is when you cross a battery, notice I'm not saying anything about current direction. When you cross a battery, if you go from the short bar to the long bar, that's a voltage increase. If you go from the long bar to the short bar, that's a voltage decrease. So those are the two rules that have to go along with this. So let's look at the circuit I have right here. And I'm first going to say, let's find the current. So that's the problem. What are I1, I2, and I3? That's the question. Here's the solution. Okay. We're using Kirchhoff's loop rule and Kirchhoff's junction rule. Okay. Darn it. Really getting aggravated with this.
Yeah, Professor, what's that resistor value at the bottom?
10.
Um, There's another resistor next to it.
Oh yeah, this one's 1. Sorry about that. I'm glad you caught me on that. That's 1.0. That's supposed to be like an internal resistance. That's why I know that one's 1.0. Thanks for that. Okay, so let's go around this loop. But for starters, I'm going to take that junction. Everybody see the little blue dot that I drew? Notice that has 3 or more wires going into it. We've got the wire that carries I3, we've got the wire that carries I2, and we've got the wire that carries I1. Kirchoff's junction rule says that the sum of the currents into the junction is equal to the sum of the currents out of the junction. So what I'm going to do is I am going to say I3, which is the current into the junction, is equal to I1 plus I2. And that is Kirchoff's junction rule. Does that make sense to everyone? We're going to call that equation 1, and we're going to make use of it later. Now I'm going to start right here, let's say at this dot, and I'm going to handle the top loop. And I'm going to do the top loop in a clockwise direction from the purple dot. Okay? So here's what I get when I traverse that. Okay, so I'm starting at that purple dot. Notice I go to the left because I want to go clockwise. So I go to the left and I go from small bar to long bar. So that's going to be a increase in voltage of 25 volts. And that's the only thing I'm going to put units on is when I do the volts. Okay. Now notice in going to the left, I'm going the same direction as I3. So the 1 ohm and the 20 ohm resistor are both going to be voltage drops. I'm going to go ahead and combine those, trying to save time, and call that 21.0 ohms times I3. Notice I'm just using V equals IR here. V equals IR tells us, and actually I should probably put that here as well. V equals IR tells us if we multiply the current I3 times resistance 21 ohms, we should get a voltage. So that's what the 21 I3 is. And notice it's minus because we went the direction of the current. Now at the blue dot, I'm going to hang a right because I said I'm doing the top loop. Does everybody follow that? So now I'm going the same direction as I2 again, only this time it's I2. And in fact, I run into a 15 ohm resistor. So that's going to represent a voltage drop again. And that's going to be 15.0 I2. Now I return to the purple dot. That means I've completed my loop. So I'm going to say that's equal to 0. And I'm going to call this equation 2. Everybody follow that? Now I'm going to do the outer loop. Outer loop clockwise and starting at the purple dot again. Okay, so I'm starting at that little purple dot. Notice this time I'm going down because I'm planning on going clockwise. Clockwise is, clockwise. like the way a non-digital clock moves. Okay, so with this one, notice I'm going against the current I1 because I1 goes from left to right in that bottom wire, and I'm going in that bottom wire from top to bottom, which ultimately ends up right to left. So this first 2 resistances, the 10 ohm and the 1 ohm, are going to make 11 ohms, but it's going to be a voltage increase. So what I'm going to write is plus 26, plus 11.0 times I1. That's the voltage increase because I'm going the opposite direction of the current. And now I hit the 40 volt battery, but notice I hit the long bar first and then the short bar. That means there's a voltage decrease. So this whole world's jacked up here. So this is going to be minus 40 volts. Okay. Now I continue upward through the blue dot, nothing happens, and then I get to the 15 ohm resistor. This time I'm going the direction of I2. So the 15 ohm resistor will be a voltage drop, and the voltage drop will be 15.0 times I2. Now I get back to my purple dot, so I can say the answer is 0. And that's equation 3. Everybody follow that? So notice I did this kind of in some sense stupidly. I wanted to make sure I traversed one current in the opposite direction so you'd understand what I meant about voltage drops and increases. And I wanted to make sure I traversed one battery in the wrong, quote unquote, wrong direction so you'd see that sometimes batteries are voltage decreases. So I've done that. Now, what I see is equation 1 is an equation for all three currents, I3, I1, and I2. Generally speaking, by the way, you've got two nodes here. That's what the two dots are. And if you subtract 1 from the number of nodes, that's how many Kirchoff's junction rule equations you should have. That's why we only have 1. But check this out. Equation 2 has, whoa, 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 whoa. Yes, equation 2 has I2 in it and I3, and equation 3 has I1 in it and I2. So what that tells me is I can solve equation 2 for I3 and it'll only be in terms of I2. And I can solve equation 3 for I2, or excuse me, for I1, and it'll only be in terms of I2. So if I put them in equation 1, I would only have I2 existing. So let's start off with equation 2. So from equation 2, I'm going to solve for I3. Hopefully y'all can follow this, but I3, if I pull it to the right-hand side, it becomes positive, and then I'm going to say equals 15.0 I2, and that's going to be a negative, and then plus 25. Now I'm going to drop the volts because it's obvious. And then, of course, I have to now divide by 21 because that was the coefficient of the I3. So I'm going to divide all this by 21.0. Now, that's okay, but what I like is to actually have just numbers or fractions or decimals or something like that. So what I want to do is I want to take that negative 15. I'm going to take that negative 15 and divide it by, oh crap, everything's gone. I'm going to take the negative 15 and divide it by 21. That's going to give me negative 0.7143. Now that's 3 sig figs divided by 3 sig figs, so I should have 1 extra sig fig there. And then I have that times I2. Now I'm going to take the 25 and divide it by 21. And that gives me 1.190. So that's 1 extra sig fig as well. I'll call this equation 2 prime. Okay. Now I'm going to take equation 3 and I'm going to solve it for I1. Now I1, if I leave it right there, it'll stay positive. So I can pull I2 to the other side. That's going to become positive. So I'll get 15.0 I2 plus the 40 when it comes over will also become positive. So that'll be plus 40. And then, of course, I've got to divide by 11. Well, again, I like my numbers. Like I said, I like them. So I'm going to take 15 and divide it by 11, which is 3 sig figs divided by 3 sig figs. So I get 1 point, stupid computer, 1.364. That's 1 extra sig fig times I2. Now I'm going to say 40 divided by 11. And that gives me plus 3.636, like that. And we can call this equation 3 prime. And actually, class just expired. I'm going to finish this up. You guys are free to go. Make sure you chat me your first and last name. I appreciate those who already did. I'll finish this up. It's going to take about 2 seconds. I'm going to plug 2' and 3' into 1. And that's how I solve it. So I can take 2', which gives me I3. That's going to be a negative 0.7143 I2 plus 1.190 is equal to, now I've got equals I1. So I1 we found was 1.364 times I2 plus 3.636. That's an extra sig fig there as well. Plus I2, which would just be plus I2. Okay. So I can combine this I2 and this I2 and then pull this I2 over here, and we'll get basically 1.3, or excuse me, 1.364 plus 1 for the I2 that's already there, plus 0.7143 for the one that was on the other side. That gives me 3.0783 I2 on the right hand side. Now I'm going to take this 3.63 and move it over here to the 636, move it over here to the left. All I have left over there is the 1.19, and the 3.636 is going to become negative when it goes over there. So I'm going to do 1.190 minus 3.636. That gives me negative 2.446. Oops. 2.44. What? Darn it. 6 like that. In this case, that is again 1 extra sig fig, and in this case, this one was actually 2 sig figs extra. So now I can say that I2 is equal to negative 2.446 divided by 3.0783. That gives me negative 0.7946. Negative 0.7946 amps. And the fact that it came out negative just means that we have chosen the wrong direction for current I2. But that also means that now we got to continue using that negative sign until we're finished using all the equations. So now that I have I2, I can plug that back into 2' to get I1 or to get I3. So now I'll say 2' gives me I3 is equal to negative 0.7143 times I2, which we just discovered was negative 0.7946 amps, and then plus 1.190. And all that should give me, so I'm going to take this negative 0.7946 times negative 0.7143. Now I'm going to take that 0.5676. I'm going to take that and add it to 1.190. And that's going to give me 1.758. And that's going to be equal to I3. I happen to know that's right, as I happen to know that the 0.7946 is also right. Now I'm going to do 3', and 3' will allow me to figure out I1. So I1 is going to equal 1.364 times I2, which was a negative 0.7946, and then plus 3.636. one extra sig fig there as well. So I'm going to take the 1.364 times negative 0.7946. That gives me negative 1.08 something. Now I'm going to add to that 3.636. That gives me 2.552. Amps to one extra sig fig, and that's going to be equal to I1. I also happen to know that one's right. And that's it, everybody. Sorry for taking so much time. Like I said, I'll try to solve that other one and post it. So the results might not be up tonight. The video will be up sometime late tonight. It usually takes on the order of an hour to upload it. So you guys are free to go. Thanks, everybody. Keep an eye out for an online test. I'm probably going to open one up, and it'll probably be due a week plus a day. So for instance, I'll probably make it available, and then it'll be due probably Wednesday night of next week. Have a good one, everybody. Sorry about the mistakes I made. Hopefully this will help everybody.
Yeah, have a good night, Younger. Hey,
You too.
stay off the Mercury tablets.
I gotta do that.
Yeah, I'll see you tomorrow morning.
All right, see you, Micah. All right, that looks like it.